Okay, today we will define a representation, but before that I want to say what is a simple superalgebra or a simple associative superalgebra. So let's start with a definition. Suppose that A is an associative or a Lie superalgebra. We say A is simple if A is not 0 and 0 and A are the only ideals of A. Our next definition. Suppose that A is a unital associative superalgebra and V with V0 as the even part and V1 as the odd part is a superspace. We know that endomorphism V0, V1 is a unital associative superalgebra. An associative superalgebra homomorphism phi from A to the unital associative superalgebra endomorphism V0, V1 is called a representation of A in V. We should mention that we always assume a representation of A in V maps the unital elements of A to the identity map over V. Okay, in this definition, we saw that what is a representation of a unital associative superalgebra A in a superspace V. We saw that it is just an associative superalgebra homomorphism from A to the non-associative superalgebra endomorphism V0, V1. In the next definition, we want to define a representation of a Lie superalgebra, and I think you should guess what should be. In fact, suppose that L is a Lie superalgebra and V equals V0 direct sum V1, where V0 is the even part and V1 is the odd part, is a superspace. A Lie superalgebra homomorphism phi from the Lie superalgebra L to the Lie superalgebra GL F V0 V1 is called a representation of L in V. Our next theorem says that there is a one-to-one correspondence between representations of a Lie superalgebra and its modules. Similarly, one can see that there is a one-to-one correspondence between representations of an associative superalgebra and its modules. In fact, there is no difference between modules and representations. If we have a module, we have a representation, and if we have a representation, we have a module. Okay, let's look at an example, the adjoint representation. Assume L equal L0 direct sum L1 is a Lie superalgebra. And define the map add from L to GLF from L to GLF L0 L1. Look at this GLF L0 L1. These two parts are the even and the odd part of a vector superspace, and we can talk about GL L0 L1. And define a map from L to GL L0 L1 by X maps to add of X, where add of X is defined to be a map from L to L, mapping Y to the bracket of XY. It is a representation of L in L. This representation is called adjoint representation of L. Our next definition, suppose that A is either an associative superalgebra or a Lie superalgebra. We also assume V and W are two A modules. A homogeneous linear homomorphism phi from V to W. We know that we assume phi is homogeneous. It means that it is either of degree 0 or of degree 1, okay? In general, phi equals phi 0 plus phi 1. And when it has degree, it means that either phi 1 is 0 or phi 0 is 0. Such a homogeneous homomorphism is called a module homomorphism if phi xv equals -1 degree phi degree x x phi v. Okay, in this equality, this guy appears. We have phi x, and whenever we change the order of two things, such a thing appears. We have phi x v, and here x phi v. We change the order of x and phi, and this guy appears. So a module homomorphism is a map satisfying phi x v equals -1 degree phi degree x x phi v. Here we have degree phi, and phi is homogeneous, so degree phi has meaning, and x is an element of V. Also, the product here is a module product in V, and this product is the module product in W. Whenever we define a homomorphism, we can talk about epimorphism, monomorphism, and so on. There is a very nice and useful relation between L modules and UL modules. Here, L is a Lie superalgebra and UL is an associative superalgebra, and we prove that there is no difference between L modules and UL modules. Suppose that L is a Lie superalgebra and pi is a representation of L in the superspace V. Okay? What we have L and a map from L to GLF V0 V1, we call it pi, and we recall the canonical map from L to UL, and also we recall the universal property of UL. We have a Lie superalgebra homomorphism to GLF V0 V1, which is endomorphism V0 V1 bar, and this is a Lie superalgebra homomorphism, and the universal property of UL gives us a homomorphism from UL to endomorphism V0 V1. So we get a unique associative superalgebra homomorphism pi tilde from UL to endomorphism V0 V1 with the property that pi tilde 1 equals 1. So we have a superalgebra homomorphism from UL to endomorphism V0 V1, and it is just a representation of UL. So we start with a representation of L and we get a representation of UL. And this representation satisfies pi tilde or iota equals pi. So we get a representation satisfying pi tilde or iota equals pi. Conversely, we can start with a representation of UL, a map, a homomorphism from UL to endomorphism V0, V1. We call it phi, and then the composition of phi and iota is a map to endomorphism V0, V1. And we can prove that this composition is a Lie superalgebra homomorphism. So we had a representation of L and we get a representation of UL. And now we have a representation of UL and we get a representation of L. And this correspondence is a one-to-one correspondence. So there is no difference between L modules and UL modules. If phi is a representation of UL in the superspace V, then phi of iota is a representation of L in V. And this correspondence is a one-to-one correspondence.
And there is a very important theorem it is PPW theorem, Poincaré-Beil-Hopwit theorem. It says that suppose that L is a Lie superalgebra and I is a totally ordered set. Assume if I is a basis for L. But I want the elements of this basis to be homogeneous. So I assume this basis contains just homogeneous element, and it is possible because L is direct sum of L0 and L1, and you know if we get a basis for L0 and get a basis for L1, the union is a basis for L because it is a direct sum. So we assume that we have a set which is a basis and the elements are homogeneous. Okay, then in fact in this theorem we want to say that how we can get a basis for UL using a basis for L. Basis as a vector space. Okay, just as a vector space. We get a basis for L as a vector space, and then one, it's I1, it's IC R1 RT when R1 RT is greater than 0. T is a positive integer, and I1 is less than up to IT, R1 up to RT are greater than 1, and of course I1 up to IT are elements of I, and there is another point that if degree of x ij is 1, then Rij is just 1. Look at this. We have a basis for UL. And what is this basis? This basis contains 1 and other elements in this form. xi1 r1 up to xit rt. This t is a positive integer. I1 up to it are elements of this I. xi1 up to xit are elements of the basis. I1 is less than I2 up to it. R1, RT are positive integer, but if one of these, for example, if xi1 is an element of L0 or an element of L1, when xi1 is an element of L1, R1 must be just 1. If one of these elements are from L1, the only possibility for R1 is just 1. Let me make a convention. Sometimes I write this in this way. It is just a convention. If I have, for example, x1, xit, r1, rt, and I let t to be 0 as well, by this one I just mean 1, okay? And also if r1, I said r1 is 0, just something power 0, I just mean 1. It is just a convention. Okay. Any question about the term?
For Lie algebras, not superalgebras, you just remove the last condition.
Yes, exactly. Yeah, it is for Lie superalgebras in general, and when we are working with Lie algebra, we don't have the L1 part, so we have this theorem, but this condition is vanished. Okay, let's look at some examples. Suppose that m and n are positive integers and set also m and n to be all Black matrices. A is m times n, m. B is n times n. And C is n times m, and B is m times n. And I want to assume that m is not n. With this property, that trace of A equals trace of D. Phi trace remains the summation of all diagonal elements, and SLMNF is the set of all black matrices such that trace of A equals trace of B. In fact, X is an element of SLFMN if supertrace of X, which is defined to be trace of A minus trace of B, is 0. You remember, SLN in non-super case was the set of all elements with trace 0. And here in the super case, we have those black matrices. For those matrices, super trace must be 0. And super trace is just trace of A minus trace of B. Okay. And clearly, if I name it G, G is G0, direct sum G1. G0 is just A0, 0B. A M times M, B N times N, and trace of A equals trace of B. And the G1 is just 0, 0, B, B. M times N, and C is N times N. And you can see that SLFMN is an ideal of GLFMN. Yesterday, I told you that when we have a Lie superalgebra, the even part is a Lie algebra, and the odd part is a module for the even parts. Okay? Set H to be the set of all diagonal matrices. If we set H in this way, then we want to find a basis for this H. We should mention that elements in H are diagonal and supertrace is 0. E equals the set H0 E11 plus E1 bar 1 bar. Again, when I put bar on a number, I mean that we are in this block. Okay? So E11, E1 bar, 1 bar, what is this? We have a matrix here. We have 1, 0, 0, and we have 1, 0, 0. Trace of this block is 1, and the trace of this block is 1. So the supertrace is 0. Okay? It's one of the elements. And the other elements are like this. ECT minus E11 and EP, which is EP bar, P bar minus E1 bar 1. When C is between 2 and m, and p is between 2 and n. We can assume that both of them are greater than 2 to be sure that we have all the this. Okay. So, one more time, G0 is a Lie algebra, and H is a subalgebra. This H is diagonal element, and so it is a subalgebra of G0. So we can consider G0 as an H module. Okay, and G1 is a G0 module. We can consider G1 as an H module as well. Okay. Define epsilon I from H to F and delta P from H to F. Epsilon I maps H0 to delta I1, maps HT to delta IT minus delta I1, and maps dP to 0. And delta P is a map, maps H0 to delta P1, maps HT to 0, and maps dQ to delta PQ minus delta P1. If we define epsilon I and delta P in this way, we get that then G0 has a weighted space decomposition state to H. G0 is direct sum G0 alpha. Alpha belongs to R0, where R0 is 0. Epsilon I minus epsilon J when I and delta P minus delta Q when I is not G and P is not Q. Also, G1 equals direct sum G1 alpha. G1 has a weighted space decomposition. G1 direct sum G1 alpha with respect to H, where R1 equals epsilon I minus delta P and delta P minus epsilon I when I is between 1 and m and P is between 1 and n. Moreover, we have 0, 0 equals H, G0 epsilon I minus epsilon J is just F EIJ G0 delta P minus delta Q is F P bar Q bar. G1 epsilon I minus delta P is just EI P bar, and G1 delta P minus epsilon I is FE P bar I. You can guess what's happening. We have some development process, and here, if it is ij position, it is for this part. If we have in PQ position, we have this part, and IP, we are here, PI, we are here, okay? And so we have this decomposition. Okay, G0 has decomposition, G1 has this decomposition, and G is G0 direct from G1, so G has a decomposition. So G equals G0 direct sum G1 equals direct sum G alpha, where R is R0, R1, and G alpha is G0 alpha if alpha is an element of R0, and it is G1 alpha if alpha is an element of R1. Okay, let's look at the shape of this topic. Look what's happening. Suppose that it is my G, and inside G we have H, right? And we have H star here. G is a leaf superalgebra, H is a subalgebra of G, and this H star does not have any algebraic structure. It is just a vector space. It's not an associative or the superalgebra or algebra. It is just a vector space. And R is a subset of this H star. And the important point is that using this R, and you can see R is just some elements of a vector space, finitely many elements of a vector space. And the point is that using this subset of a vector space, we can get a lot of information about G and H. Or it's better to say about G, because H is a subset of G, and it is just a diagonal matrices. The structure of G in general, because it's just an example, in general, we have G and a subset of that G, and then we get H star and R, and using this R, we can get something about G, something that I'm talking about is in general, not just for this example, okay? But you can see in this example that such a thing is happening, okay? And now we want to have a closer look at this R. Let's have a definition. A subset P of R is called a parabolic partition if plus P intersection with R is a subset of P. We say P is closed. P plus P intersection R is a subset of P. R is P union minus P, and P intersection to minus P is just 0. Okay, if such a thing happens, we say that P is a parabolic partition. And the second definition is subset of R is called a parabolic set if plus P intersection to R is a subset of P, and R is P union minus P. Clearly, when we have a parabolic set, when we have a parabolic partition, we have a parabolic set. But I will show you some examples of parabolic sets which are not parabolic partitions. Okay, when we say we have a partition, the set P and minus P have just intersection 0. But for parabolic set, this can be other elements. For example, the set 0, epsilon I minus epsilon j, delta P minus delta Q, epsilon I minus delta P, when I is less than j and P is less than Q, it is a parabolic partition. And 0, epsilon I minus epsilon j, delta P minus delta Q, plus minus epsilon I minus delta P is a parabolic set. Okay? If you make the sum of two of these elements and again are an element of R, you can see that it is again an element of P, and clearly for this set, if we call it P, P intersection minus P is just 0, but for this one, the intersection of P and minus P is the element of this one. Okay, so it is a parabolic set, which is not a parabolic partition. And the parabolic sets and parabolic partitions are very important in representation theory. Okay. Define kappa from G times G to F maps xy to supertrace xy. X and y are elements of G, so x and y are some matrices. They are square matrices of the same dimensions, so xy has meaning, and supertrace of xy has meaning. So we define kappa, mapping xy to supertrace xy, and as an exercise, show that kappa AB equals -1 degree A degree B kappa BA. AB are elements of G0 or G1. So kappa ABC equals kappa ABC, and it is something that we call it to be invariant. Kappa is non-degenerate. And the last one is that G0, G1 is 0. If we omit this guy, kappa AB equals kappa BA, we call it symmetric. And when this guy appears, we say supersymmetric. So kappa is supersymmetric, it is invariant, it is non-degenerate, and satisfying this property. G0, G1 is 0, we call it even. We say the form kappa is even. In fact, we have G0 direct sum G1, and if we get an element of G0 and element of G1, it is 0. I can explain you why we call it even, because you look at this, we have G0, G0, G1, G1, G0, G1, plus G1, G0. If we consider this part as a superspace, like this, and then we are in F. F is F0, direct sum F1, when F1 is just 0. Right? And it is like a map from a superspace to superspace. So we can say it is of degree 0 or degree 1. And because of that, we call it even. It means that it is just of degree 0. Right? Okay. So we start with a G, and now we can form another superalgebra. Define G hat to be G tensor FC plus minus 1, direct sum C, direct sum FC, direct sum FP. It is just a two-dimensional vector space. Okay? You're familiar with this, yeah? We start with a simple algebra and form this, and now we start with an especially superalgebra, SLMNF, and then we make this one. Okay? and bracket of C with G hat 0, bracket of B is tensor Cn to the n is tensor Cn, bracket of BD to be 0, and bracket of X tensor Cn y tensor Cn to the bracket of xy tensor Cn plus n delta n plus m0 kappa xy. Then G hat together with this Lie bracket is a Lie superalgebra. As an exercise, show that G, which is SLFMN, is a simple Lie superalgebra. Okay? In non-super case, I told you when we have a simple Lie algebra, then we can form G hat, and this G hat is a Lie algebra that we call it affine Lie algebra. And now we start with a simple Lie superalgebra, this specific one at present, and then we form G hat, and this G hat is also some Lie superalgebra called an affine Lie superalgebra. Okay, it is an example of affine Lie superalgebras. Okay. Just look at this. I told you that it is a Lie superalgebra. And what is the even part? Even part is just G0, tensor Laurent polynomial, direct sum FC, FT, and G hat 1 is G1 tensor FT plus minus 1. In fact, this part is of the degree 0. Okay? Let me write it here. G hat 0 is G0 FC plus minus 1, FC and G hat 1 is G1 FC plus minus 1. Okay, let's look at G hat. We have G hat, which is G tensor FT plus minus 1, direct sum FC, direct sum FD. But beside that, G has a beta space decomposition. So we have here summation of G alpha, when alpha is an element of R, tensor FC plus minus 1, direct sum FC, direct sum FD. So I can write it in this way, and maybe it's better to write it as a direct sum. And what we have it is H tensor 1, direct sum FC, direct sum FT, maybe it's better to write it in this way. Then G alpha tensor Tn, direct sum Fc, direct sum Fd, when alpha is an element of R and N is an element of Z, because Ft plus minus is direct sum of Ftn. Okay, and now I can write it in this way. H, when alpha is 0, G 0 is just H. We have H tensor 1 Fc Fd. We have direct sum of H tensor Tn. And we have direct sum G alpha tensor Tn. Alpha belongs to R, but not 0, and N belongs to Z. Right? Okay. And we call it H. We identify H tensor 1 with H. So instead of H tensor 1, I just write H and set H to be H direct sum Fc, direct sum Fd. So we have G hat equals H direct sum H tensor Tn when N is not 0, direct sum G alpha tensor Tn. Alpha is an element of R but not 0, and N is an element of Z. Okay. We have such kind of decomposition. And now we extend alpha. Alpha is an element of R, and R is a subset of H star. We extend alpha as an element of H star to H star. Compare H and H in the capital H and the simple, the curved H. Compare these two. We have Fc and Fd here. And alpha is an element of H star. I can extend it to an element of the dual space of H just by mapping C and D to 0. Okay? And define delta from H to F, maps D to 1, and H direct sum Fc to 0. Oh, D to 1. We can verify that G hat has a weighted space decomposition with respect to H G hat gamma is H if gamma is 0. G hat gamma is H tensor Tn when gamma is M delta for sum n belongs to Z minus 0, and G hat gamma is G alpha tensor Tn when gamma is alpha plus n delta. Alpha belongs to R, but not 0. And R hat is just R plus Z delta. So G hat has a basis space decomposition with respect to H. The support is R hat, and R hat is just R plus Z delta. And G hat gamma, if gamma is 0 is H, if gamma is N delta is H tensor Tn, and if gamma is alpha plus N delta, when alpha is not 0, it is G alpha tensor Tn. You can check it easily. It's not very hard. You just should write it. Okay, I think there is something wrong with this. The message is you have been signed out. Or maybe. Okay. But the message says you have been signed out because you are currently signed in and in another device. I don't know, maybe. Oh, you are in the Zoom, yeah?
Yeah, I'm just checking what happened.
Yeah. And it's work. Okay. Sabrina, maybe it's okay. Okay. Yeah.
Is it recording?
I think so. Yeah, it is. Okay, and for this R hat, we again can define parabolic sets and parabolic partitions. Okay. So I don't write down the definition. It is the same as the definition parabolic set and parabolic partition for R. Just as an example, let P be a parabolic set of of R hats. And it is very easy to verify. Just some sketch. Look at this. If alpha plus m delta, when alpha is an element of R and m is an element of C, if it is an element of pi hat, then look at this. P contains 0. Okay, so all elements of Z delta are elements of P hat. Okay. Then what we get? Alpha plus m delta is an element of P hat, and we know minus m delta is 0 plus m delta is an element of P hat. So alpha, which is alpha plus m delta plus minus m delta, is an element of R hat intersection with P plus P hat plus P hat. And what we want to prove? We want to prove that okay, P is a parabolic set of R, and we want to show that P hat. Okay, we want to show that P hat. P is a parabolic set, and we want to show that P hat is a parabolic set. If gamma and eta are elements of P hat, then there exists alpha and beta belong to P, and Mn belong to Z, such that gamma is alpha plus m delta, and eta is beta plus n delta. Now, if gamma plus eta are so this is P. Now, if gamma plus eta are elements of R hat, what we have? We have alpha plus beta plus m plus n delta is an element of R hat. Then we get alpha plus beta is an element of R hat. So what we have two elements of P, and the summation, and the summation is an element of R. But we suppose that P is a parabolic set, so this implies that alpha plus beta is an element of P. So when alpha plus beta is an element of P, alpha plus beta plus m plus n delta, by definition, is an element of P hat. Okay, so one of the properties that we should verify was that P hat plus P hat intersection R hat is an element of P hat, and we saw it. And it is just one part. Please do the other part by yourself. I just showed that P hat plus P hat intersection R hat is a subset of P hat, and you can show that R hat is exactly P hat minus P hat. It is your exercise, and it is something that I did. Okay, so when we have a parabolic set of R, we can get a parabolic set of R hats. Okay. And you can show that if hat is a parabolic set of R hat and delta is an element of P hat intersection minus P hat, then there is a parabolic set of R such that P hat equals P plus Z delta. So in fact, that example will cover all parabolic subsets of R hat, but those parabolic subsets with this condition. If delta is an element of P hat intersection minus P hat, then for sure there is a parabolic set of R such that P hat is P plus Z delta. Let's look at another definition. A subset E of R hat is called I call it pi. It's better, right? A subset pi of R hat is called a base of R hat if pi is linearly independent and it is something usual. It is linearly independent, but the second property is very important. R hat is a subset of span of pi over z greater than or equal 0 union span pi greater than or less than or equal 0. What does it mean? You know, pi is linearly independent. And what is this condition? Each element of R hat can be written as a linear combination of elements of pi. Okay? But the coefficient at first all integers, okay? And not only integers, all of them are non-negative or all of them are non-positive. Okay? And this property is very important. I can give you one of the bases that R hat has. Epsilon 1 minus epsilon 2 up to epsilon m minus 1 minus epsilon m, epsilon m minus delta 1 minus delta 2 up to delta n minus 1 minus delta n, and delta minus epsilon 1 minus delta n is a basis of R.
So these are all positive linear combinations here.
Here, yeah, it is, you know, the only, each element of R hat, suppose that that element is not 0, that element can be written as a linear combination of elements of pi, and all coefficients are positive or non-positive, or all of them are non-negative. Let's look at one of these. Suppose that, for example, look at this. I write epsilon I minus epsilon j. Let me first write. What was r hat. R hat was I plus 3 delta. And what was R? R was 0, epsilon I minus epsilon j, delta P minus delta Q, and plus minus epsilon I minus delta Q. Right? It is our R hat. Look at, for example, epsilon I minus epsilon j when I is less than j, okay? And we can write it in this way. Epsilon I minus epsilon I plus 1. Epsilon j minus 1 minus epsilon j. Yeah? You write epsilon I minus epsilon j as a linear combination of elements of this phi, and all coefficients that are not 0 are positive, right? And exactly epsilon j minus epsilon I is the opposite, so all the coefficients are negative. And it happens for all of the elements. You can check, for example, if we have, for example, delta minus epsilon 2 plus delta 3 minus delta 3, for example, if we have something like this, what we can write is this. Delta minus epsilon 1 minus delta n, and minus epsilon 2 plus delta 3 plus epsilon 1 minus delta n. So I can write it in this way, delta minus epsilon 1 minus delta n plus epsilon 1 minus epsilon 2 plus delta 3 minus delta n, for example. And again, you write it as a summation of 3 elements of pi, and all non-zero coefficient is positive, right? And you can check it, and please check it by yourself and show that it is really a basis. A basis. Okay. And the point is that and I want to tell you something that I forgot. The only element that belongs to this part and this part is 0. 0 is the only element that contains in this. Okay. The point is that suppose that pi is a base of R hat. Then R hat intersection S and B is a parabolic partition.
Do you mean span pi?
Yes, yes. Thanks. And it is clear, right? Because we have R hat is a subspace of S span pi union S span pi. So it implies that R hat equals S span pi intersection R hat union S span pi intersection R hat. And this is just opposite of this one, right? And so we have the first condition that R hat is P hat intersection union minus P hat. And what was the other one? And also we should prove that P hat plus P hat intersection R hat is a subset of P hat. But if you have an element of P hat, it is a summation of, it is a linear combination of elements of pi, and the coefficients are non-negative. And also another element is in P hat, so that element is again an element which is linear combination of pi, and the coefficients are non-negative. So if summation is an element of R hat, again it is a summation, it's a linear combination of elements of pi, and the coefficients are non-negative. So the second property is easily follows. So and as I told you, the only element which is an element of this part and this part is 0. So we have a parabolic set that P, I call it P, and it's better to this. And the only element of P and minus P is just 0, because the only element of the only element in the intersection of this part and this part is 0. Okay? So P is a parabolic partition of R hats. Okay, it seems that I need to drink some water because and now what we can do using parabolic sets or partitions. At first, we start with parabolic partitions. Okay. Assume P hat is a parabolic partition of R hats. So we have R hat equals P hat union minus P hat. P hat plus P hat intersection with R hat is a subset of P hat, and P hat intersection minus P hat is just 0. We can then it implies that R hat is disjoint union of pi hat minus 0, 0, and pi hat minus pi hat minus 0. We have such decomposition, and these decompositions are disjoint. Okay? And then we can, using this decomposition for R hat, we can take a decomposition for G hat. It implies that G hat is direct sum of G hat gamma when gamma is an element of R hat. And as R hat has this decomposition, we have this decomposition. Direct sum G alpha G hat gamma. Gamma is an element of P hat minus 0, direct sum G hat 0, but we know that G hat 0 was H. And this part, direct sum G hat gamma, when gamma is an element of minus P hat minus 0. Okay. And let's call it G hat plus. And this part, G hat minus. So, G hat plus, direct sum H, direct sum G hat minus. And because of the property that P hat has, I remind you, P hat plus B hat intersection R hat is a subset of P hat. You can get that G hat plus is a subalgebra of G hat. And it is obvious because if you have two elements of P hat minus 0 and the summation is again an element of R hat, then that element is an element of P hat minus 0. Okay? If it's not clear, please tell me to explain more. If you need, I can explain it more to you. If alpha and beta are two elements of P hat minus 0, we look at G hat alpha, G hat beta. But it is easy to see that it is a subset of G hat alpha plus beta. If alpha plus beta is not an element of R hat, then G hat alpha plus beta is 0, and so this bracket is 0. But if alpha plus beta is an element of R hat, because of the property that P hat has, it means that alpha plus beta is an element of P hat, and for sure it's not 0. So G hat alpha plus beta is a subset of G hat plus, and so the bracket of G alpha, G beta is a subset of G hat plus. It means that if you have the bracket of two elements of G hat plus, you get an element of G hat plus. That means that G hat plus is a subalgebra of G hat. G hat plus is a subalgebra of G hat. G hat plus direct sum H is also a subalgebra of G hat. And also G hat minus is a subalgebra of G hat. G hat plus, G hat minus, and G hat plus direct sum H, all of them are subalgebras of G hat. Okay, and you remember in the last lecture, I told you when we have a subalgebra of a Lie superalgebra, universal enveloping algebra can be embedded in the bigger one, right? So B is a subalgebra of G hat, so UB can be considered as a subalgebra of UG hat. Okay. Now I want to introduce you a representation. I want to form a representation for this G hat, and I construct that representation for you. Look at this edge. Dimension of edge is finite, and edge, you remember, edge is contains diagonal matrices. So the bracket of two elements of edge is 0. It means that edge is abelian. Edge is an abelian finite dimensional Lie algebra. You remember, edge is just subalgebra of G0. It is a subset of the even part, and G0 is a Lie algebra, so H is just a Lie algebra. H is a finite dimensional abelian subalgebra of a Lie algebra. And you remember, I told you about the irreducible representation of an abelian Lie algebra, which is a finite dimensional as well. You remember, each representation is determined by just a functional. Okay? So, assume lambda is an element of H star, and suppose FB is the irreducible one-dimensional H module corresponding to lambda. That is HV equals lambda HV for all H belongs to H. Right? Now, extend this action to B. In fact, define look at this. We have a module for H, and I want to have a module of B. Okay, I define this now. B, FB to FB, which maps X, B. If X is an element of H, we know what is it. It is lambda X3. And if X is an element of G hat class, I define it to be 0. Right? And it is very easy to verify that this is really a module. Okay? Now, the interesting point is coming up now, because what we have, Look at this. We had G hat minus H, G hat plus. We want to have a module on G hat. Till now, we have a module on this part, okay? And something that we do is this. Remember, UB is a subalgebra of UG hat. And you remember, when we have a B module, we have a UB module. At the beginning of this section, I told you that there is no difference between modules of a Lie superalgebra and the modules for the universal enveloping algebra. So when we have a B module, in fact, we have a UB module. So I have C, I have F3, which is a module I have a module for UB, and UB is a subalgebra of UG hat. So I can make this tensor product, right? And for sure, it is a UG hat module with the natural product. And again, when we have a UG hat module, we have a G hat module, right? The module action is in this way: UG hat times M maps to M. That's X A tensor V maps to XA tensor V. Right? Completely natural. So we start with an irreducible module. I remind you, we have this decomposition. H, G hat minus. We start with a module over this part, extended to this part, completely, very easily, just put 0 when X is an element of G hat plus, and then for this tensor product, and we get a module for G hat. In fact, at first we get a module for UG hat, but if there is no difference between G hat modules and UG hat modules, we get a module for G hat. But we always like to have irreducible ones. We are looking for the irreducible module, and this module, it's not necessarily irreducible, but we can deal with this as well. Let's look at it again. What we have. G hat is G hat plus direct sum H, direct sum G hat minus, and G hat plus is direct sum G hat alpha when alpha is an element of P hat minus 0, and G hat minus is direct sum G hat alpha when alpha is an element of minus P hat minus 0. And I just remind you that R equals minus R, and so R hat is just minus R hat. Okay, choose a basis EI because it is countable. I consider a basis EI of the vector space G hat plus and a basis Fi of the vector space G hat minus such that, look at this, G hat plus is direct sum of some subspaces. And these subspaces, except for when alpha is not 0, that we have here, this one. Let me write to remind you. You remember, G hat beta plus n delta was just G beta tensor Tn, right? So if beta is not 0, this is just one dimension, okay? And if beta is 0, G hat and delta was H tensor Tn, right? So all of them are finite dimensional and most of them are one dimensional. So if we choose a basis for each of them and then union all of them, we get a basis for G hat plus, right? I select a basis in the way that for each I, there exists alpha I belong to P hat minus 0 such that EI is an element of G hat alpha I. And Fi is an element of G hat minus alpha. Right? This basis contains elements which are elements of these vector spaces. Okay. And now, and fix a basis H1 up to HL of H. So we have a basis for this part, we have a basis for this, we have a basis for this, so we have a base for G hat. So EI, Fi, H1 up to HL is a basis for the vector space G hat. And using PBW theorem, we get a basis for UG hat. So by PBW theorem, and you remember, when I want to talk about PBW theorem, I need a totally ordered set. So I need an order on this element, and I choose the order in the way that you will see. Okay. EI1, EIT, H1, HL, FJ1, FJ1, JS, M1 MS, P1 PL, K1 KT. That here, with the convention that I told you, I allow these powers to be 0 as well, because I don't write 1 here. If all of them are 0, I suppose that that one is 1, right? And here, M1, MS, P1, PL, K1, KT are some positive or positive integer or 0, and also J1, JS, I1, IC are elements of Z, but we just remember if one of them is of degree 1, the power must be 0 or 1. And if one of the Fi1 up to Fjc, Js, E1, EI1 up to EIT is of degree 1, then the power is 0 or 1. It is a basis for UG hat. Okay. What we have, M is UG hat, tensor UB, and then FV. And now we have a basis for UG hat. It is S panel X tensor B over F, when X is an element of this basis that I call it, for example, Z. Right? Because this UG hat, each element of UG hat is a linear combination of elements of this form, so M is a linear span of the elements of this, right? Okay, but let's look at one of these. If we look at Fj1, M1 up to Fjs, Ms, H1, P1, HL, PL, EI1, K1, EIT, KT, tensor B. Please be careful. Look at this. EI1 up to EIT are elements of the, I write here what we had, just to remember. We had G hat minus H, G hat minus plus, and this is B, right? And EI1 up to EIT are elements of G hat plus, which are elements of B. And our tensor product is on UB, right? So we can pass this part into this part. But you remember, the module action of the elements of G hat plus on B was 0, right? So we get 0 if at least one of them is not 0. So in this set, we just have S span of X tensor B, not all elements of Z. But we can omit this part, right? And suppose that we omit this part. What happens for this part? we have H1 up to HL. Again, H1 up to HL are elements of H, and H is a subset of V. And again, we can pass H1 up to HL to this V. But we know the module action of H over V is just a scalar product of V. So we just get again V. It means that M is a linear span of X tensor V, but not all elements of Z, just those elements of F parts, right? Okay. It is a span of F over X tensor V when X is Fj1 M1, Fjs J1 up to Js are elements of Z. J1 is less than up to Js. M1 and S are greater than 0 or 0, and if one of the Fj1 up to Fjs is of degree 1, then the corresponding power is 0 or 1. And I think these are also, I should write here that J1 is less than Js, I1 is less than I2. Okay? So F is something like this, right? But let's again look at these elements. Oh, it is 12. You were a very good student, and I cannot realize that how the time is passing. Okay, but please let me complete this. Yeah. Okay. Suppose I or J is an element of Z, and consider Fj Fjv. For simplicity, I write it just Fjv. I identify this with this, okay? Just to simplify the notation. And look at this, for each H belonging to HFGV, what is this? It is a module over G hat. So it is H Fj V plus Fj HV, right? And you remember, I told you that Fj is an element of G hat alpha j, so it is alpha j H Fj V, and it is lambda HV, so we have lambda H Fj V. So we have alpha j plus lambda H Fj V. In fact, V is an element of M lambda, and Fjv is an element of M lambda minus alpha j, right? You remember the definition of MU. MU was all elements of M such that Hx is mu Hx for all H. V is an element of M lambda, and Fjv is an element of M lambda minus alpha j. And you can see that similarly, Fj1 R1 up to Fjs RSV is an element of M lambda minus R1 J alpha J1 minus RS alpha JS. So M is direct sum of M mu. Mu is a subset of supports M, or this writes H star here. And support of M, according to something that we wrote, support of M is a subset of lambda minus R1 alpha J1 till minus RC alpha JT when C is greater than 0 or it is 0, and R1 up to RT are this. It means that it is subset of lambda plus span over non-positive integers of p hat minus z. You remember alpha j1 up to alpha jt are elements of p hat minus 0. So support of M is a subset of this. And the first thing that we get is that M has a weighted space decomposition. Till now, we start with a module for H, and then we form a module for G hat, and this module has a weighted space decomposition, and at least I'll show you that support of M is satisfied this property. And sorry, it is after 12. Okay. Thank you, everybody. Have a good time, and let's start tomorrow.